Okay, so welcome to this second lecture of this week. So now that we have finished the mathematical modeling part, we're going to start with a topic called time domain analysis. The name of the topic is a little bit misleading because what time domain analysis does is to make a relationship or find a relationship between the Laplace domain quantities and time domain quantities. And in this topic, we're going to be looking at the time functions of the outputs, and we're going to be making a connection between the Laplace domain quantities like pole zero locations and, for example, the order of the system, etc., with the output behavior. So by looking at the poles of a system, we will be able to say, for example, what the output of a system to some specific input would look like. For this purpose, we are going to be using some specific input types that is called unit step input or unit ramp input, and we are going to be investigating the outputs of systems for these simple inputs. As you might remember, unit step input is just a constant input, and unit ramp signal is just a linear signal increasing towards infinity. By giving these simple inputs to the systems, we will be able to characterize the performance measures for some control systems. For example, if we want a control system to settle at some time instant, we are going to be asking the question, what should be the parameters of a controller such that the output settles in 2 seconds to a constant for unit step input? That is going to be one of the questions that we are going to be answering, and one of the tasks that we are going to achieve in time domain analysis. So our topic is time domain analysis. So the aim here will be threefold. We are going to have three aims here. Calculate y of t output for different u of t, for different inputs. Okay? This is going to be our first aim. So we have a system, it has an input u of t and it has an output y of t. We're going to be asking the question, what would be the output of the system for this specific input? And for the specific inputs, we will use unit step, unit ramp functions. The second aim is probably more important. Understand the relationship between the transfer function parameters and the output behavior. So what is a transfer function parameter? It can be a pole or a zero of a system. So these are parameters of the transfer functions. Or it can be one of the coefficients in any of the polynomials in the numerator or denominator of that transfer function. So we will be asking, what is the effect of such parameters on the output behavior? For example, what will happen if I change one of the parameters between some constant and another constant? So what happens if I change the parameter value in an interval? Then what is going to happen to the output? For example, we're going to see that the poles are going to be really important, and we're going to see, for example, if I change the pole locations, we will be able to predict the behavior of the output, how it is going to change after a change in the pole positions. So this is the main aim of the time domain analysis, making a relationship, finding out the relationships between the transfer function parameters and the output behavior, or between time domain quantities and Laplace domain quantities. And the third aim is going to be to determine some performance measures. For control systems. For example, we are going to be asking the question, how much time does a controller take for the output to settle at some constant value? This is going to be called the settling time of a control system, and it's going to be a performance measure that we would be using in assessing the performance of control systems. So if the settling time is small, it is going to be good for us. If the settling time is large, then it's going to be bad for us. So suppose that I would like to be controlling the temperature in this room, and suppose that I'm controlling it using an air conditioner. And suppose that we are currently at 20 degrees, it's really cold here actually, so our heating system does not work yet. So suppose that it's now 20 degrees, and suppose that I want it to be at 27 degrees. And if the air conditioner really takes 2 hours or 2 days to be able to reach the desired temperature value, then I would say that that air conditioner is really a bad air conditioner, because its settling time is really too large. So for large settling times we would really would not like, and small settling times we would want from a control system. Or there are also other types of performance measures. We're going to see that some control systems or some controllers would cause some oscillations in the output, and we really do not like a lot of oscillations in the output. Suppose that we are thinking about a cruise control system. Suppose that we would like to bring the velocity of a car from a low value to a high value. In that case, if the velocity makes some oscillations while trying to reach a desired value, then it would be really bad for the comfort of the driver or for the comfort of the passengers. So we really do not want the velocity signal of a car to make oscillations. So we are going to be using some performance measures for measuring the amount of oscillations in a system as well. So we are going to sometimes we are going to see that some signals are going to go over above the desired value, and then they will come back. So we are going to be calling that type of behavior in a control system. We are going to be measuring it using a performance measure called maximum overshoot. And we would really like the maximum overshoot of a cruise controller to be small, for example. So these are going to be performance measures. But here we are going to go from the simple to the complicated tasks. So the first thing that we're going to consider is going to be the simplest dynamic systems that we can consider. And these are going to be the first order systems. So we are first going to consider first order systems, and then we are going to go into the second order systems. And actually these are going to be all, because at the end we are going to see that the outputs of all order systems, all different orders of systems, can be written as a linear combination of first order systems outputs and the second order systems outputs. So we're going to be considering only these two types of systems, first order and second order systems, and we will see at the end that we can express the outputs of all different order systems using these two different behaviors for the systems. So when I say a first order system, what do you understand? Remember, we talked about the order of a transfer function or order of a system by looking at a transfer function, and it was related to the maximum power of s in the denominator polynomial. So this first order system tells us that the maximum power of s in the denominator in the transfer function is just actually equal to 1. That is what we understand by the first order system. What is the simplest first order system? I can actually have the simplest first order system looking like this, 1 over S. So this system is a first order system because the order of the denominator polynomial is 1. Therefore, this is a first order system, and I will claim that this is actually an integrator. So I have to explain that statement. What does it mean? So what is a transfer function? Here the transfer function of the system is g of s, and it is equal to 1 over s. And we know that a transfer function is nothing but the ratio of the output Laplace transform to the input Laplace transform. So we have y of s over u of s, and if I write this equation in the following form, s times y of s is equal to u of s. Okay? So we see here that if I go into time domain, I'm going to obtain the equation y dot is equal to u. So the derivative of the output is equal to the input. What does this mean for the output? So this means that if I integrate both sides here, then this derivative is going to be cancelled by the integral, and then y is going to be the integral of the input. Okay? So y here, y of t can be written as minus infinity to t u of t dt. Maybe I should put t prime to change the integration variable and the limit. They should not be the same. So this is my y of t for this simple system. So this is just like an integrator, as you see. The output is the integral of the input, and that is why sometimes we show this system with just this, just an integration sign and the output. Okay? So these are equivalent systems in control systems. So remember, multiplication with s is a derivative operator in Laplace domain, and division by s, it is what 1 over s is doing, is just an integration. So there is also an intuition of that form. So this system is a first order system, and where are its poles and zeros? We see that it doesn't have any zeros, but it has a single pole at 0, at the origin. So if I make a pole zero plot, I would see that this system has a single pole at s equals to 0 at origin, and it doesn't have any zeros. So what can this system represent? This is a mathematical idealization somehow, and what type of real system does an integrator represent? Actually, the answer is much more common than what you would think. So suppose that I have a mass. Okay, this is mass, and I will assume that the mass value is 1 kilogram. Okay, so suppose that I am applying a force to this mass, and suppose that we are measuring the velocity of the mass, which is x dot. Okay, so that is my system. So velocity is the output. So input is the force I apply, and the output is the velocity of the mass, which is x dot. Okay, let us calculate the transfer function of such a system. This is one of the simplest systems that we can encounter in mathematical modeling. What are the equations? M times x double dot is going to be equal to the net force applied onto the mass. So instead of x double dot here, I'm going to write just v dot. Okay, because x double dot is acceleration, and which is equal to v dot. So m times acceleration is going to be the net force. There is no friction or no spring force here. There is only this input force that is applied to this mass, which is going to be F. And I have already told you that m is 1 kilogram. So this is equal to 1, so I can actually neglect this in this equation. So I would have for this system, the output-input relationship would be output dot is equal to the input. But that is what I have said here. This is the same equation as the earlier one. So here, let me pass this equation into Laplace domain. S times V of S is equal to F of S. And what is the transfer function for this system? G of S is just the ratio of the Laplace transform of the output to the input. Output here is V, and the input is F of S. And from this equation, if you calculate the output to the input Laplace transformation, you would see that it is 1 over S. So a single mass is actually the single mass system. From the force you apply to the velocity you obtain is just a simple integrator. Okay, a mass of 1 kilogram. All right. So every mass that you see around is an integrator. You apply a force to it, and mass actually integrates that force, and then it gives you a velocity. All right. So you can think about every mass that you see around as integrators in this way. All right. So it is not really an uncommon system. An integrator is everywhere. As I walk down here in front of the board, I am applying some force with my muscles to the mass of myself. I think it's a lot. So then my mass is actually converting the forces that my muscles are applying. They are converting them to some velocity and then to some position. Okay? So there is an integrator everywhere that we look at with masses. So now we're going to be doing a very simple task, and that task is going to be calculating some outputs for this simple system to some simple inputs. Okay? So let us say the example. And in this example, we are going to compute the step response. Sometimes we call it unit step response of the system. G of S is equal to 1 of S. Okay? So what do we mean by unit step response? It is the response, the output of the system when we give to it the unit step function as an input. Okay? So we know that the output y of s over u of s for the system is g of s, which is equal to 1 over s. Okay? And when I look at this equation, then y of s, the Laplace transform of the output, is the transfer function times the input Laplace transformation. Okay? When we are asked to calculate the step response of a system, then what we need to do is we need to calculate the output of the system, y of t, to the unit step input. It is the input of the system, which is the unit step function. Okay? And in this equation, I need to calculate what is y of t. So y of t is going to be the Laplace inverse of capital Y of s. And I know that y of s is g of s times u of s. Okay? This is Laplace inverse of g of s times u of s. So when we are required to calculate the response of a system to some input, what we need to do is we need to multiply the transfer function of that system with the input Laplace transform, and we need to take the inverse Laplace transformation. That is going to give us the output. Okay? Now let us try to apply this principle to calculating the unit step response for this system simple integrator 1 over s. So for solving such an example, what I have to do is to write the transfer function of the system, which is 1 over s, and I need to write the Laplace transform of the input as well. And in this case, I know that u of t is unit step input. Okay? And what does this mean? This means that my input is going to be this function. It is equal to 1, so u of t, unit step input, is 1 for t larger than or equal to 0. That is my unit step input. And what is the Laplace transform of this function? We have seen in our investigation of the Laplace transformation, this was the first function for which we calculated the Laplace transform. And we have seen that it is u of s is equal to, oh, it is already here, sorry. We have seen that the Laplace transform of such a function is 1 over s as well. All right? And calculating the unit step response means that I need to multiply these two Laplace transforms here, and y of s, the Laplace transform of the output, would become the multiplication of these two functions. And it is going to be 1 over s squared. All right? And now I have to take the inverse Laplace transformation of that function. 1 over s squared in a Laplace domain, we have again seen this in our investigation of the Laplace transformation. And if I calculate y of t, which is the inverse Laplace transformation of this function, it is just going to be t for t larger than or equal to 0. Okay? This means that unit step response or step response of the system that we are considering, which is the integrator, is the unit ramp function. Okay? So this is defined as unit ramp function. Okay? And if I try to draw it, you might remember this from earlier. So I have y of t, and it is just like this, and the slope here is 1. Okay? So we are going to be doing such calculations over and over in time domain analysis. So we are going to start with a system, and then we are going to be asking what is the unit step response of this system. And then we are going to improve our question just a little bit. We are going to make it more complicated. What is the unit ramp response of this system? And what would that mean? So this is the unit step response of the system. And what would be unit ramp response? So it would be just the response of the system to a unit ramp input. Okay? Then the input Laplace transformation is going to be this one, and I will multiply it with g of s, and that would give me the Laplace transformation of the output, and I would be taking the inverse Laplace transformation of that in order to be able to calculate the unit ramp response. Okay? So when I actually qualify the word response with unit step or unit ramp, that is, or unit acceleration sometimes, it is going to mean that I'm meaning the response of the system to that specific type of simple input. Okay? And unit step response will be the response of the system to the unit step function as the input, and unit ramp response would be the response of the system to the unit ramp function as the input. Okay? So this example is already complete. Now I'm going to go into more complicated first order systems. So this was probably the simplest first order system, which is equal to 1 over s. Just a simple integrator. But there are also more complicated first order systems, and these are going to be looking like a over s minus b. Okay, this is also a first order system, and you see that it is a little bit more complicated than the integrator system, which is 1 over S. So now we have a pole location at S equals to B, and we don't have 0 if A is not a 0 here. So now how can I have such a system? And in order to be able to explain the reasoning for such a system, I will use this mass system here, which takes the force as the input and it gives me the velocity as the output. Okay, here is what I'm going to do. So this is my mass system. It is 1 over S as a transfer function. This is the force I give to the mass, and this is the velocity I get. It is the output. I will call the output both as V and Y. Y is the conventional output variable, and here in this case Y is equal to V, the velocity of the mass, and the input of the system is just F. Suppose that I would like to come up with a feedback system such that I would like to make the velocity of the mass equal to a desired velocity. Okay? I would like to make the velocity of the mass equal to a desired velocity, and I would like to do this using a form of feedback. Okay? Here is what I'm going to do. I would have some reference input, R of t. This is going to be the desired velocity of the mass. And I would put here a subtractor. And I would subtract the actual velocity, which is this thing. I will subtract the actual velocity from the desired velocity. Okay? Then I'm going to apply a force which is proportional to the error signal here to the mass. Okay? This is a feedback system which would try to bring the velocity of the mass to a constant reference or to a reference signal R of t. I would like to make the actual velocity of the mass as close to the reference signal as possible. Okay? And this is such a system. So here, this type of controller here is called a proportional controller in control. Proportional controller. It is the system between the error signal and the input of the actual system that we would like to control. Okay? This difference, we usually call it as E of t. Okay? It is the error signal, E of t, error signal, and R of t is the reference signal. So we would like to bring the actual velocity of the mass as close to the reference signal as possible. Suppose that my reference signal is constant. Okay? Suppose that the reference velocity is 90 kilometers per hour. Okay? So suppose that this is my reference velocity, and what is going to, and here I'm assuming k is positive. Okay? So suppose that the actual velocity of the mass is 70 kilometers per hour. Suppose that v of 0 or y of 0 is equal to 70 kilometers per hour. Okay? In that case, what is going to happen? So the initial value of V0 is 70 kilometers, and this is 90 kilometers per hour. And when I do this subtraction, the difference is going to be positive because the actual velocity is smaller than the reference velocity. So the error signal is going to be positive. It is going to be multiplied by k, which is a positive constant, and therefore I will apply a positive force onto the mass. Applying a positive force onto this mass is going to increase its velocity. Okay? So applying a positive force onto the mass is going to increase its velocity so that the new velocity at an infinitesimal time instant later is going to be larger than 70 kilometers per hour. Okay? Suppose that after some time instant, the velocity became 75 kilometers per hour. Then what is going to happen is that this error becomes smaller and the force you apply becomes smaller. Okay? Suppose that the velocity came to the 90 kilometers per hour, exactly the desired value. In that case, I would have the subtraction result. The error signal will be equal to 0. It is going to be multiplied by k, which is going to give me 0 force to be applied onto the mass. And what is going to be the result of that? It is going to be that I will apply 0 force onto the mass, which means that there will be neither acceleration nor deceleration of the mass, which will mean that the velocity is going to remain constant. Okay? What happens if this V0 is actually larger than the desired value? Suppose that the initial velocity value of the mass is larger than the desired velocity. In that case, this difference becomes negative, and that means a negative error signal. And negative error signal is going to be multiplied by this positive constant, which is going to give me a negative force. And a negative force means that I will try to make the mass decelerate. Okay? I will make the mass move with a slower velocity or smaller velocity. Okay? In that case, mass will start slowing down. Okay? This value is going to be smaller and smaller as time passes, and at exactly the time instant at which this velocity value reaches 90 kilometers per hour, I will start applying 0 force onto the mass, and which is going to make the velocity of the mass constant. So this is a feedback system. Actually, it is a cruise control system that is used in the cars. So this is cruise control. And this is our car system, which is represented by a single integrator. Here you might argue that this is not a realistic model of the car because there is no friction here. But still, it's an idealized model of the car, and this is an idealized cruise control system. And here, the controller that we are using, the constant multiplier here that we put between the error and the input of the actual system is called the controller. And because there is just a proportionality constant here, there is a single multiplier here, this controller is called proportional controller. And this K here is called the proportional controller gain. Okay? So K is gain of the P controller. Okay? We abbreviate proportional controller as P controller, and K is the gain of the P controller. So now, what happens when we form such a feedback system? I can actually draw a block around this system, and then when I connect this feedback loop, this integrator system turns into another system with the input R of t and the output Y of t here. Okay? So I have the actual system here, which is the open loop system. This 1 over S is my open loop system, and we connected it in a feedback loop, which gave us a closed loop system. And in this case, the input of the closed loop system is this reference signal R of t, and the output of the system is still Y of t, which is the velocity of the car that we would like to control. So now, how can I examine such a system? So I know that when I connect this feedback loop in this way, we get a new system. And then we will have a closed loop system which is going to have a transfer function that is going to be equal to the transfer function of this feedback loop. Okay? So before I calculate the transfer function of the feedback loop, I will replace this parameter k with the parameter 1 over t. Okay? Suppose that I define another parameter t which is related to k in this manner. Okay? So t is positive and k is positive and k is equal to 1 over t. Sometimes it is easier to work with this capital T, and that is what we are going to use here. Just remember that 1 over t is just equal to k. It's an equivalent parameter. If I know t, I know k. If I know k, then I know t. So these are equivalent parameterizations of the same system. So now what is the closed loop transfer function of such a feedback loop? Let us calculate that. G closed loop of S is equal to, we know how to calculate the overall transfer function of such a feedback loop. We first write the forward transfer function, forward path transfer function, divided by 1 plus everything in the loop. Okay? What is the forward path transfer function? It is the multiplication of these two blocks, and it is 1 over Ts. Okay? Divided by 1 plus, remember this is a negative feedback loop here, and I have everything in the loop. The feedback path has the transfer function 1, and that means that everything in the loop is going to be just the forward path transfer function. It's going to be the same as the numerator here, 1 plus Ts. And that actually gives us 1 over Ts plus 1 as the closed loop transfer function of this system. And here I will just do something like this. So I will take T parentheses in the denominator, which is going to give me this. Okay? But this is equal to 1 over T divided by S plus 1 over T. Okay? So this is my transfer function. And you see that it's a first order transfer function because the largest power of S in the denominator is 1, and we are going to have a single pole resulting from this. So if I make a pole zero plot for this system, it doesn't have any zeros, and it is having a pole at minus 1 over t. Okay? And since 1 over t is just equal to k, the pole is at minus k. Okay? It's the same position. So now this is a first order system, and the task that we are going to achieve is that I'm going to be calculating the output of this closed loop system to unit step function. Okay? So as the input, as the reference signal, we are going to use the unit step function. That is R of t, reference signal, 1. So I have t here. So R of t is unit step function. What does this mean? This means that we would like the velocity of the mass to come from 0 initial condition to 1 kilometer per hour. Okay? So this is the reference signal. So we want the mass to follow we want the mass velocity to follow this signal, which means that we want the velocity of the mass to be equal to 1 kilometers per hour. Okay? The initial velocity of the mass is going to be 0 kilometers per hour. So actually the output, we would want the output to come from 0 and to settle at the desired value 1. All right? So here let us calculate the unit step response. This unit is just optional here. Sometimes we just say step response of the system. Okay? So remember our theory. Y of S in this case, we are calculating the output of the closed loop system to unit step input. And in this case, our R of t, the input of the system, is going to be the unit step function, which is going to have the Laplace transformation 1 over s. And the transfer function of the system, closed loop system, is this one, which is a first order system, 1 over t over s plus 1 over t. So this is going to be the Laplace transform of the output. All right? So now I'm going to be writing this in a more familiar form. So this is going to be 1 over t s plus 1 over t, which is much more familiar to us. It's the same thing, okay? So now I have to take the inverse Laplace transformation of this Laplace transform. Okay? How can I do that? This Laplace transform has a pole at s equals to 0 and s equals to minus 1 over t. One of the poles is coming from the input 1 over s, the unit step input. The other pole is coming from the transfer function of the system. All right? And I need to take the inverse Laplace transformation of this Laplace transform. Remember how we handled such problems at the beginning of the course. So we have to make here a partial fraction expansion. I need to write this as a over s plus b over s plus 1 over t. Okay? So now let us equate the denominators here. So I would have as plus 1 over t plus bs divided by s plus 1 over t. So I would have here a plus bs plus a over t divided by s plus 1 over t. So now I have to equate the numerators of this transfer function and this transfer function. Okay? We see that a plus b is equal to 0 and a over t is equal to 1 over t. All right? Since t is non-zero, I can cancel it, which gives a equals to 1, and from the first equation I have b equals to minus 1. All right? That means that my Laplace transformation, the y of s, is 1 over s, a is 1, and b is minus 1, minus 1 over s plus 1 over t. Okay? So now I have to take the inverse Laplace transformation of this function. And remember, e to the at had the Laplace transformation 1 over s minus a. Okay? So we need to remember such a Laplace transformation in order to be able to take the inverse Laplace transformation here. So now let us write our output, the unit step response. Y of t is equal to inverse Laplace transformation of this term is 1, it is the unit step function, minus, if I use this fact here, in order to be able to take, what am I going to use for a? A is going to be minus 1 over t, so therefore we will have here e to the minus t over t as our inverse Laplace transformation. And this is true for t larger than or equal to 0. This is our unit step response for this system. Okay? Now let us try to observe such an output. So I have my input given like this. This is my unit step input. That is my reference signal, and I would like to draw here the unit step response on that figure. So this exponential is constantly decaying, and at t equals to 0 it's equal to 1, which means that the output is equal to 0 at t equals to 0. Okay? If I substitute t equals to 0, then I would have y of 0 is equal to 0. So our output is going to start from here, and what is going to happen then? This e to the minus t over t is going to get smaller and smaller as time progresses, and the output is going to be larger and larger. And what is going to happen as time t goes to infinity? What is going to happen is that as t goes to infinity, this exponential is going to decay to 0, and my output is going to be equal to 1. So my output is going to be coming in this manner, and it's going to converge to the value 1 here. Okay? So this is my unit step response. What does that mean? This means that when I start my cruise control system at 0 velocity, and when I give it a reference, then the output is going to start approaching the desired value without any oscillations, and it is going to reach the desired value as time t goes to infinity, and it's going to remain there. Okay? So this is what this unit step response would tell me. So if I put here some labels, this blue curve is my y of t, which is the unit step response for this system. So now what we are going to be considering here is what is the error value of such a controller. Okay, what does that mean? So we are going to consider something called the steady state error. In this control. Or we are going to be asking the same question for different controllers as well. What is the steady state error of this controller? It is going to be related to this signal E of t. Remember, this was called the error signal, and the steady state error is going to be defined as limit as time goes to infinity, the value of this error signal. Sometimes this is infinity, sometimes this is finite and non-zero, and sometimes this is equal to 0. But what about in this case? What is the final value of this error signal? What is the steady state error? In this case, let us calculate this. E of t is the difference between the reference signal and the output signal. Okay? It is r of t minus y of t. Okay? R of t is equal to 1 in the case of unit step response, and y of t is given as this function, minus 1 minus e to the minus t over t. Okay? And in this case, these ones are going to be cancelling, and I would have e of t is equal to e to the minus t over capital T. Okay? So what happens as time goes to infinity to this error signal? Actually, I'm seeing it already in this curve. As time passes, the difference between the reference signal and the output is getting smaller and smaller, and it is getting towards 0. Okay? So the steady state error for this system is limit as t goes to infinity, e of t is equal to 0. So such a control system has 0 steady state error, which means that this controller, this is the proportional controller that we are using, is achieving its aim in a very good manner as time goes to infinity. Okay? So this means that this controller is achieving its aim asymptotically as time goes to infinity. Okay? So, but really, is this really that good? Because depending on the capital T value, the behavior of this response can change its behavior. If T is larger, how would this response be changing? So let us consider that. So I will try to show you two different step responses for the same system for different t values. So this is my input, t, and this is my original, let us say this is my original response here for some candidate t value. But what is going to happen if t becomes larger? Suppose that I change this controller parameter such that t becomes larger and k becomes smaller. If t is larger, then k becomes smaller. Okay? What happens if I change the t value? If I make t larger, how would this response change? You see here that this t is the parameter of our controller, or this k is the parameter of our controller. So by changing t, we are changing the parameter of our controller. And by changing t, we might get a better response, or we might get a worse response. So we might ask which t value is better for us. Okay? Let us try to understand this. So if I make t larger, then what would happen to this exponential? If I make t larger, is this exponential going to decay faster or slower? If I make t larger, then this exponential is going to decay more slowly. Okay? If we make t larger, then exponential will decay more slowly. And we know that this behavior is due to the decaying of the exponential. If exponential decays more slowly, then the response would be looking like this. A slower decay of the exponential would give us something like this, a slower response. Okay? So in this case, t has increased. All right? And what happens if I make t smaller? In that case, the exponential would decay faster, and my response would be looking like this. A faster decaying exponential would give me a faster convergence. Okay? So this is smaller t. All right? When t becomes smaller, the response becomes faster, and when t becomes larger, the response becomes slower. All right? So then this means that, and you see that all three of these responses are reaching to the same desired value. Okay? So in terms of the steady state error, all of these three responses are the same. But in some way, these responses should be different. And that difference is what we call in the transient of the response, transient part of the response. So somehow we call this part of these responses as the transient part, and this part, when we have the convergence, as the steady state part. Steady state part. Okay? So the steady state error is related to the steady state part of the response when time goes to infinity. And the transient part is related to how we reach the steady state part, how fast we reach the steady state part. Okay? So here we see that this parameter t, as long as it is positive, it does not affect the steady state performance of the system. The steady state error is equal to 0, whatever t is, as long as it is positive. But t is changing the transient behavior of the system. Okay? And if t becomes smaller, then we have a faster control system. The convergence becomes faster. If t is larger, we have a slower control system. So this parameter t, which scales the small t in the exponential, is called the time constant of the system. So this capital T is called the time constant for the system. Okay? And as the time constant of the system becomes large, then the system becomes slower, and as the time constant of the system becomes small, this means that the system becomes faster. In general, we assume that a system reaches steady state at 3 to 4 time constants. Okay? Sometimes, well, this is called the settling time. The time interval, or the amount of time for which the system reaches steady state, is called the settling time. And we show the settling time with Ts, and it is either 3t, depending on some application, or sometimes it is defined as 4t. Okay? So we assume that these exponentials decay sufficiently for us to reach the final value, depending on the time constant of a system. Okay? The amount of time that is required for a system to reach its steady state is called the settling time. And it is usually defined either as 3 time constants or 4 time constants. Okay? Depending on the application, this actually changes. But here, we are always relating the settling time of a system, which determines how fast a control system is determined by the time constant of the system, and there is a proportionality constant here, either 3 or 4, depending on the application. Okay? So what is good for us? A smaller settling time or a larger settling time? Which is better for us? We usually want smaller settling times. So the smaller Ts is, the better the control system. Okay? So here I can write Ts, the settling time, the amount of time required for a control system to reach steady state. Okay? It is either 3 time constants or 4 time constants. Now the only thing that I'm going to investigate here in this simple example is the pole locations. So remember, this system has a single pole, okay? And this single pole at -1/t. Okay? That is our pole position. All right? Now, what does this mean? What does it mean for this system to be slower? If the system is slower, then time constant is large. Okay? If time constant is large, then this means that the pole is moving towards the imaginary axis. Okay? This is increasing t, and this is decreasing t. Okay? So this is when t is decreasing. What about the settling time? Settling time is when t is increasing, the settling time is increasing. When t is decreasing, the settling time is decreasing. Okay? In this direction, control system is better because Ts is smaller. And when the pole moves in that direction, control system becomes worse because the settling time becomes larger and larger, as pole moves towards the imaginary axis. So what we are going to say is that the transient performance of a system is dependent on how close the poles of the system are to the imaginary axis. If the poles of the system are close to the imaginary axis, then that control system becomes very, very slow. If the poles of the system are further away from the imaginary axis, if they are towards the left, then that control system is better. So this is the aim of time domain analysis. Okay? What are we doing here? Pole location is a Laplace domain quantity. Okay? This is the Laplace domain quantity which we can see on this pole zero plot. Okay? And by looking at this pole location, we can actually say that if this pole location comes towards the right, if it approaches the imaginary axis, then what happens is that the control system becomes slower. I would have a slower response. And if it is exactly on the imaginary axis, then you would see here that the control system is never reaching the desired value. So if the pole on the other hand goes to the left, then if it gets further away from the imaginary axis, then what is happening is that the control system becomes faster. So poles further away from the imaginary axis to the left are good for us, and poles closer to the imaginary axis would be bad for us in terms of control. Okay? So this was the unit step response. As a final thing in this lecture, we are going to see the unit ramp response. What would be the unit ramp response for such a system? This was unit step response. So let us look at unit ramp response. In this case, our reference signal is going to be the unit ramp function. What is the unit ramp function? R of t is t for t larger than or equal to 0. So if I try to draw it, the unit ramp function is something like this. So that is our input, okay? And here the slope is 1. And what is unit ramp response? It is the response of this system to this input. And what is the Laplace transform of the input for the unit ramp input? In that case, we have just seen, and we have seen earlier, that unit ramp function has the Laplace transform 1 over s squared. Okay? So now let us calculate unit ramp response. We're going to do the same thing here. So y of s is going to be g closed loop of s times the input Laplace transformation. Remember, sometimes I call the input u of s, and sometimes when it is closed loop like this, I usually call the input as r of t and its Laplace transformation as r of s. When it's an open loop system, I usually call the input u of t and its Laplace transformation as u of s. But here, the input of this closed loop system is the reference signal, and I'm calling it r of s. So this is 1 over s squared, and g closed loop of s is what we have already calculated, 1 over t over s plus 1 over t. Okay? So now I have to calculate, so this is my y of s. If I put it in a more familiar form, it is 1 over t, s squared, s plus 1 over t. It looks like this, and in order to calculate the unit ramp response, I need to take the inverse Laplace transformation of that transfer function, or Laplace transformation. So now let us apply partial fraction expansion to this. So remember, the first term is going to be s squared, and the second term is going to be s plus 1 over t. And remember what we were doing. In the partial fraction expansion, if I have an s squared term here, then what I would do here is I put a first order polynomial here, as plus b, and here I need to put a 0th order polynomial, which is going to c. All right? Now let us equate the denominators. So as plus b times s plus 1 over t, and I have plus c s squared divided by s squared s plus 1 over t. Okay? So now I will do the multiplication here in the numerator. So as squared plus I have a over ts plus bs plus b over t plus cs squared divided by s squared s plus 1 over t. Okay? That is equal to collecting the terms, similar terms, a plus c s squared plus a over t plus b s plus b over t divided by s squared s plus 1 over t. All right? Sorry for my bad writing here. So this is s squared. So now I have calculated the numerator polynomial. All I have to do is to equate the numerators. The numerator here on the left is 1 over t. So I would have b over t is equal to 1 over t. T's are going to cancel, so b is equal to 1. And the coefficients of s and s squared will be equal to 0. A over t plus b is equal to 0. B is 1, so a is equal to minus t. And a plus c is equal to 0. A is minus t and c is equal to t. Okay? So we have found the required coefficients. Now let us substitute them back into y of s. So I have as plus b. A is minus t s plus b is 1 divided by s squared, and c is plus t over s plus 1 over t. All right? So now let us try to take the inverse Laplace transformation of these terms. So here an interesting thing is that minus ts over s squared is going to be minus t times 1 over s, and I have plus 1 over s squared plus t over s plus 1 over t. Okay? Now this is unit step function, 1 over s. 1 over s squared is the unit ramp function, and t over s plus 1 over t is nothing but an exponential which is multiplied by t. So let us write y of t here. Y of t is minus t times unit step, which is 1, plus t, and plus capital T times e to the minus t over capital T. This is true for t larger than or equal to 0. All right? So now let me try to arrange the terms here just a little bit, just in a better way. So I will write this as y of t. I will take the t term first, so it is t, and I would have a minus parentheses in capital T. I have 1 minus e to the minus t over capital T. Okay? So this is for t larger than or equal to 0. This is our unit ramp response. Unit ramp response. Or just ramp response. Okay? These are the same thing. Now, how does this thing look like? So here, let us look at this. You have to keep in mind that unit ramp response, unit step response, they would all start at 0. Okay? So I would have here, because we are assuming 0 initial conditions when we are calculating them. So what happens when t is equal to 0? When t is equal to 0, this term is equal to 0. This is like the unit step response, okay? So it is at time t is equal to 0, the exponential is 1, so this term is 0. And I would have t is equal to 0. So at t is equal to 0, we have the response is equal to 0. What about the response as t goes to infinity? As t goes to infinity, I would have this term equals to 0, so we would have t minus capital T. Okay? So as t goes to infinity, we are going to be capital T below the main ramp function here. Okay? So, and there are no oscillations here, there are only decaying exponentials. So what we're going to do is that as time is equal to 0, we start at the same point as the ramp function, and as time t goes to infinity, we converge to the ramp function with a distance with the original ramp function equal to t. Okay? So this difference here that I drove here is just capital T. Okay? So our unit ramp response as time goes to infinity will be capital T below the actual unit ramp, which is our input. Okay? So this is our unit ramp response. And now let us look at it is transient and steady state characteristics. So here, when I look at this expression here, I see that we have again an exponential with time constant t. So we would have some settling time which is equal to 3 or 4 time constants here. So in terms of settling time, nothing changes. But what about the steady state error? Steady state error is limit of E of t, which is R of t minus the actual output, Y of t. Okay? And I have E of t is equal to, R of t is t, it's somewhere, t minus, I will subtract the actual output, minus t plus capital T, 1 minus e to the minus t over capital T. These t's are cancelling, so our error signal is t times 1 e to the minus t over capital T. And the steady state error is the limit of this function as t goes to infinity. And that is going to be, this exponential is going to be 0 as time goes to infinity, and the answer is going to be t. So we see that for unit step input, this system did not have any steady state error. But for unit ramp input, this closed loop system had some non-zero steady state error, which is equal to t. Okay? So in this case, our response is not converging to the input as time goes to infinity. There is always a gap. There will always remain a gap between the input and our response here. And this is our steady state error. Okay? So what are we going to do if we want a smaller steady state error for this system? This controller parameter we can adjust. Okay? So in order to have a smaller steady state error, what we need to do is that we need to make t, capital T, smaller, okay? Or capital K larger, all right? So a system can have a zero steady state error for some inputs, and for some inputs it might have non-zero steady state error. Then this is determining the steady state performance of this control system for unit ramp input. And if we wanted to have a better performance, we would need to make capital T smaller. What about the transient performance? in terms of the transient performance, if we make capital T smaller, we will have a faster convergence to this asymptotic behavior. Okay, so that is going to be the same criterion here. We need to make capital T smaller to have a better system in terms of both transient response and in terms of the steady state response. In terms of both transient performance, this convergence part to the asymptotic behavior, and in terms of both the steady state performance, this difference, we need to make T smaller. So here you see again that this T is actually a Laplace domain quantity. It's a parameter of the Laplace transformation. Okay? So it is a parameter of the closed loop transfer function. This capital T is such a parameter. And in time domain analysis, what we do is that we actually establish a relationship between this Laplace domain parameter and the time domain response that we see at the output. Okay? And we understand what type of changes happen to the output when we change this Laplace domain parameter. It is actually this T determines the pole position, which is also a Laplace domain quantity. Okay? So this actually completes the first order systems, and I haven't told you one important thing here. So here I have seen that whatever type of input that I gave this system, unit step input, unit ramp input, I have seen only some type of convergence without any oscillation. Okay? So whatever I did here, I gave the system unit step, unit ramp, and the responses that I have observed only contained decaying exponentials. And why did this happen? This happened because these first order systems would only have a single real pole. Okay? So this first order system, this closed loop system, had only a real pole in the negative real, in the open left half plane. Okay? We always had a real pole in the left half plane. And that is why we did not see any oscillations in these responses. So this was really related to the fact that this system was a first order system. We only have a single pole, and that single pole has to be on the real axis. Okay? Since we only have real poles, we only have either decaying exponentials or growing exponentials. Okay? That is why we didn't see any oscillations for this system. So what is necessary for a system to result in oscillations in their step response or in their ramp response? We need to have complex poles, okay? And this can only happen with second order systems or higher order systems. So the good thing about a first order system is that it can never result in an oscillation in its step response or ramp response. We always see a convergence or a direct divergence if the poles are on the right half plane. Okay? The oscillatory behavior would only appear with complex poles, and complex poles would only appear in second order or higher order systems. Therefore, first order systems are really good systems in that they don't have any oscillatory behavior. We are going to see when we start with the second order systems, we would see oscillatory behavior for some complex pole locations. And that is really going to cause a lot of problems sometimes, and that's going to be good for some other times. But this completes the first order systems, and that leaves us the second order systems for the next lecture. So I would like to thank you for watching again. Bye-bye.